Okay, so guys, this is the last type of related rates problem we're going to do. It's one that involves a cone, so let's just take a look at what we have here. Okay, so this is last year, so the name has changed for this year, but so we have a right circular cone that's 10 meters across the top and 10 meters deep, so let me draw that out. Okay, 10 meters across the top, okay, 6 meters deep. Okay, so the radius is going to be 5 because it's 10 all the way across. Alright, the 10 meters across is the diameter. So the radius is going to be 5. Okay, and she pours water into it at a rate of 10 cubic meters per minute. Okay, so if we're thinking about the dimensions for this, the important ones are going to be radius, height, and volume. And the volume is changing at 10. Okay. And so we decide to find the rate of change of the depth. Okay, that's dh dt. Rate of change of the depth when it's 4 meters deep. Okay, so we don't have anything about the rate of change of the radius. We don't have the radius, right? For ourselves, we don't have the volume. We have a lot of things missing here. Now remember, this 6 and this 5, this just tells us the original cone. It's not telling us actually what the water's information is. Okay, so if we write an equation, and you may or may not remember that the volume of a cone is 1/3 area of the base times height, otherwise known as 1/3 pi r squared h. Okay, when we look at that equation there, we can see that we have both a radius and a height that are missing, and we don't have any information. And the thing about this is, it's not like a cylinder where you're going to have something constant. If we're thinking about this, here's our water right here. Okay, as you put more water in it, the radius and the height are both changing. So if it's deeper, then the deeper it is, then the bigger the radius is going to be. The less water there, and the smaller the radius is. So both the radius and the height, neither one's constant here. All right, so if we were to take the derivative, we'd have to use the product rule, which we don't really want to do. Okay, but notice how we have no information about the r. It would be really nice if we can get rid of the r, and we can. And here's how we can. Okay, if you look at the blue that I drew in there, and you highlight it with a triangle, right? For those of you there that were here or in class on Friday, remember that we used similar triangles, and we're going to use that trick again to this. So it's kind of like that, and now we have a similar triangle between the water and the container. Okay, and with similar triangles, we set up a proportion. So the radius of the blue is to the radius of the cone. The height of the water is to the height of the cone. Okay, so we have that ratio that we set up, and hopefully you remember something about ratios back from geometry days. Okay, if I cross multiply, I'll get that 6r equals 5h. Okay, now remember, I have nothing about r, so I'm going to try to get rid of r. Right, so we're going to try to substitute out. Okay, so I'm going to solve this one for r. Right. So since I'm trying to solve for h, I have to keep that one around. There's nothing here, so that's why that one's got to go. So if I look at my volume equation, I'm going to take the r and I'm going to replace it with 5/6 h squared. Okay. Now notice this, I haven't taken the derivative. I'm just setting this up. Right. Sorry about the printer in the background there. Okay. That's okay. So we have this, and it's going to become 25 over 108 pi, and I have the h cubed at the end. So notice that I've just, by using my similar triangles here, I've created a new equation that no longer has the radius in it. Okay. Now this is what I'll take the derivative. And remember, the derivative in terms of time. So 25 times 25 over 108 times 3, that's going to nicely cancel out. Alright, the 108 and the 3 are going to cancel, like I have, pi h squared dh dt. Okay, now if you just went and did this as 25 over 108 pi times 3h squared dh dt, you would have seen that 3 and that those are reducing, so they've been just fine. Okay, At this point, I've taken my derivative. Let's see what I can plug in. I can plug in that 10 for the change in the volume. Okay, and it's increasing. She's pouring water into it. That's why it's positive there. So just want to double check that. Yep, it's positive. Okay, I have 25 over 36. I'm going to put that pi up here. Do I have the height? I have the height. I can plug that in. And I have dH dt. Okay, I'm going to try to reduce this one first here. Right, both of these can be divided by 4. So I'm going to have 10 equals 100 pi over 9 dH dt. And then when I move this to the other side, that's going to then give me, and I'm going to go up here, because I ran out of space. Right? That means I'm going to be multiplying by the reciprocal. Notice the pi is in the denominator now. That's going to nicely reduce. So I'll have 9 over 10 pi, and units are going to be meters per minute. Okay? So the tricky part about this one is just at the very beginning, we have to set up that ratio there for the similar triangle. So as you look at my work, right, as I post results, then just kind of, if you're having trouble with it, look at that part there, because that's usually where people get messed up.